talks and conference presentation Q&A sessions given by successful and famous people, one of the most common types of questions posed is, what would you tell yourself to make yourself, more famous, rich, successful, or happy? What advice would you give to your younger self? Usually the answers given to these questions are something like, work harder than everyone else, or follow your dreams. Full disclosure, I'm not rich or famous enough for anyone to have ever actually asked me these questions. But as an astronomer studying faraway stars and planets, I think the best, most useful advice I could have really used as a young kid would have been detailed instructions on how to discover the world's first extrasolar planet. This would have cemented my younger self as a legendary researcher for finding the first planet outside my solar system. Here's myself with my Nobel Prize and the telescope I use to find it. So what exactly would I tell myself? First, I would instruct myself to somehow procure a moderately sized telescope. One with about an aperture size of a foot should be sufficient, but if a larger one is available, the bigger the better. Then I would tell myself to get some sort of camera and put it on the viewing port of the telescope. Both the telescope and camera could be purchased for relatively cheap. No need to go to NASA or the National Science Foundation asking for millions of dollars in grants. Once I have this apparatus, my younger self would need to spend the next few weeks or months making brightness measurements of many stars in a wide field of the sky. Plotting stellar brightnesses over time would, with some luck, reveal what's called an extrasolar planet transit, which is a signal indicated by a slight dimming of the observed star as the planet revolving around that star crosses in front of the disk and blocks out some of the light. Now this may sound pretty overly simplistic, and in some ways it is, but over the past 2 decades or so, this exoplanet transit method has revealed thousands of planets discovered by a wide variety of instruments, from backyard telescopes used by citizen scientists to giant space observatories run by international collaborations of research universities and space agencies. We humans are obsessed with discovery and the prospects of new and exciting worlds. And exoplanet science really gets at some of these deep-level human questions of where we come from, and of course, are we alone? Speaking of are we alone, if you've ever seen the great television show Ancient Aliens on the History Channel, or if you've had a crazy uncle that believes he was kidnapped by aliens, you know that humankind loves to think of fried-out theories of other worlds and the aliens that live on them. For hundreds of years, scientists, philosophers, and science fiction writers have speculated that planets similar to those of our solar system could exist around the other stars of the universe. However, during these ancient times, there is no way of actually knowing if these hypotheses were true. The detection and study of exoplanets required the development of technologies like the telescope and precise cameras. But wait, if you think about it, telescopes and cameras have existed for many decades now. So why did it take until all the way to the cusp of the 21st century for us to finally get the first evidence of extrasolar planets, planets outside our solar system? Why weren't these planets found immediately after the creation of the telescope and the camera? Somewhere back here. I think the answer to this question has something to do with how difficult it is to think outside the box. The planets of our solar system have been studied for thousands of years now and are therefore understood quite well. On first glance then, we had a bias that planets revolving around stars other than our sun should arrange themselves kind of like our solar system. This means that during the hunt for extrasolar planets, we were looking for small, low-mass terrestrial planets very close into the parent star. This would correspond to our solar system planets of Mercury, Venus, Earth, and Mars. Meanwhile, giant massive planets like Jupiter and Saturn were predicted to be much, much further away from their parent star. In this paradigm that all planetary systems should be set up basically like our own, the instruments developed through the 20th century wouldn't have had the necessary precision to make exoplanet discoveries. This is because these small, low-mass planets close in were too light to be detectable, whereas the large, high-mass planets far away were too far away to make big differences on host star observations and reveal themselves. The concept that large, high-mass planets like Jupiter could exist right next to their parent stars was deemed very unlikely. But actually, these so-called hot Jupiter-type exoplanets, giant planets right next to their parent stars, were the first type of planet discovered. And they were found by complete accident by people who weren't even looking for them. In the mid-90s, two scientists from the University of Geneva Observatory named Michel Mayor and Didier Queloz were using a small telescope in the south of France to study binary star systems. They employed a technique known as Doppler velocity to measure the orbits of these stars. Due to the Doppler effect, as the star's orbit pulls it towards and away from the Earth, we'd see the starlight at a slightly redder color if the star is moving away from Earth, and a slightly bluer color if the star is moving towards the Earth. This is the same sort of idea that makes a police or ambulance siren sound at a higher pitch when it's moving towards you. By plotting many stars' Doppler velocities over time, Mayor and Queloz hoped to understand the fraction of stars born into binary star systems. But what they ended up finding was the first evidence of an extrasolar planet outside of our solar system. This planet was eventually called the really inspiring name 51 Pegasi b. The Doppler velocity measurements of the star 51 Pegasi are shown here. As the planet 51 Pegasi b gravitationally pulls the star in its orbit away from the Earth, we see that light at a slightly lower frequency, or redshifted. As the star comes back around in its orbit and the planet starts pulling that star towards us, we see that frequency at a slightly higher level, or blue shifted. The gravitational dance of the planet and star manifests itself as a sinusoid wave, and studying the properties of this wave, such as the wavelength and the amplitude, reveal things about the planet's orbit and the planet's size. But the most interesting part of this plot to me is revealed by looking at the data error bars. Look at how dang small they are compared with the massive size of the Doppler velocity signal. You know, it seems to me that this discovery, a Nobel Prize-winning discovery of the first exoplanet around a solar-type star, was hiding in plain sight, even for the relatively modest instruments used in this work. To put this monumental discovery into more context, let's take a brief detour and look at another Nobel Prize-winning discovery, the first detection of gravitational waves by the giant collaborations of physicists known as LIGO and Virgo. The detectors built by these collaborations were truly literal massive feats of engineering, taking more than 50 years and thousands of scientists from around the world to complete. The detectors were built to test one of Einstein's predictions from his theories of general relativity, the existence of gravitational waves which propagate through space-time at the speed of light as a result of extremely energetic cosmic events. Finally, in 2015, many decades after Einstein published his theories, it was announced that gravitational waves produced by merging black holes on the other side of the universe shifted space-time around the detectors by a tiny amount, less than the size of an atom, producing this signal. The match between the observed signal, the jagged line, and the smooth curve of what theories predicted a gravitational wave signal to look like proved the existence of gravitational waves and led to a massive explosion in gravitational wave astrophysics, in addition to the Nobel Prize in 2017. Let's now look at the qualitative differences between the LIGO discovery plot of gravitational waves and the discovery plot of 51 Pegasi b, the first exoplanet around a solar-type star. The discovery of the first exoplanet similarly led to a giant explosion in extrasolar planet astrophysics, in addition to a Nobel Prize, this time in 2019. But the difference is that the discovery of 51 Pegasi b was hiding in plain sight for normal instruments that, pretty much anyone can get their hands on, if you're an astronomer. Whereas, to make the LIGO detection of gravitational waves, thousands of scientists had to go past the edge of physics and engineering to make the discovery, and even then needed to work for years to be sure that their detection was significant against the massive amount of noise in the data. It really makes you think about what other detections, what other discoveries in physics and astronomy could be made with a slight change in perspective. Exoplanets is a really interesting, fascinating, fast-growing, cutting-edge field of astronomy. And although more than 5,000 exoplanets have been discovered so far, as of Tuesday, the actual study into the details of these exoplanets has proven to be quite a frustrating endeavor. You know, the main goal, according to numerous NASA press releases and Decatur reports, is the discovery of an Earth-like, habitable exoplanet. And with a seemingly endless amount of real estate in the universe, and 5,000 planets discovered so far, how is it that we haven't found one yet? You know, where are these guys hiding? Currently, the best method we have for determining exoplanet habitability is to look at measurements of exoplanet atmospheres. So let's take a look into the science and see just how insanely difficult it is to detect and characterize exoatmospheres. I'll give two examples of this. So the first example is actually a project that I had a part in a couple years ago. Obviously, since I had a part in it, it didn't work. But here's a failed experiment I tried to detect an exoplanet around the hot Jupiter-type planet TRES-3b. Trying to detect an exoplanet atmosphere. I used a small telescope in Maui, Hawaii, to look at a transit event of TRES-3b in two different wavelengths of light, and looked for evidence of blue light scattering in the atmosphere of the exoplanet. If there was an exoplanet atmosphere scattering blue light present, I would expect that the planet would look slightly larger in blue light than in red light. This would result, therefore, in a deeper transit signal in the blue light compared with the transit signal in the red. This experiment was inconclusive, though, as the light curves in blue and red light looked almost the same, you know, within the error bars of the data. But, you know, maybe if we spend $1 billion and we build a telescope and launch it in a rocket into space, we'll get a better look at what's going on with exoplanet atmospheres. Some of the best data ever concerning exoplanet atmospheres was taken in 2007 of another hot Jupiter-type exoplanet, HD 189733b. Now, we really got to work on these names. Yeah. I guess there's 5,000. Using the Spitzer Space Telescope, an instrument costing more than $700 million, the spectrum of an exoplanet was taken, revealing its temperature as well as some information about what elements could be in its atmosphere. Here's the spectrum, where the points are the amount of light received by Spitzer's instruments at each wavelength, and the line through the points is the spectrum of a model atmosphere made to kind of fit the data. Now, I don't know about you, but looking at this fit, it seems a little shaky, especially compared to the discovery plot of 51 Pegasi b with a beautiful model fitting the data. It seems that after spending $1 billion, you know, we're still quite far away from learning what's going on with exoplanet atmospheres. As I'm sure some of you know, though, we recently launched the biggest, baddest space telescope ever, the JWST, which completed its alignment last week, and hopefully will give more information about what's going on in exoplanet atmospheres. But, you know, I'll believe it when I see it. No Earth-like exoplanets have been discovered so far, but there are many stars around which our sister planet could be hiding. Astronomers' best estimates say there are around 300 million stars in our galaxy, and over 200 billion galaxies in the observable universe. This means there's almost 1 billion trillion stars in the known universe, and our sun is just one of 1 billion trillion similar objects. These are astronomically large numbers, but to put them into perspective, the classic analogy is to say that there are more stars in the known universe than there are grains of sand in all the world's oceans. Out of all these beautiful planetary systems, though, none discovered so far fulfill the same life-giving qualities that we enjoy here on Earth. Earth's particular composition of atmosphere, we have nitrogen, oxygen, carbon dioxide, argon, other trace gases. This atmosphere really makes it possible for all forms of life to exist. You know, we let plants, animals, bacteria, and us make energy from the sun or from digesting other organic molecules. Earth is also the perfect size for its atmosphere to hold on to Earth's gravity, preventing the life-giving gases from drifting off into interplanetary space. This is actually what we think happened with the atmospheres of Mercury and with Mars. Earth formed at the perfect distance away from the sun to allow for the presence of liquid water on its surface, an essential ingredient for the development and sustainment of life as we know it. It's so critical that we call exoplanet habitable zones, quote unquote, by the distance away from the parent star that liquid water could exist. As a bonus, Earth's particular composition of molten nickel iron core rotates, giving rise to a magnetic field which shields us from deadly solar particles that can zap our DNA, make life on Earth impossible. This delicate balance of life we enjoy on Earth really depends, though, on our care of Earth's atmosphere. And with the current rate of greenhouse gas production, the temperature and composition of our atmosphere may change completely within the next few human lifetimes. Studying exoplanets has really revealed the improbability of an environment like Earth and informed the importance of taking care of our home's atmosphere. There is no planet B or any backup for Earth, so we might have to take into account some out-of-the-box solutions for protecting and preserving our home world. Thank you.